Chapter 3, Section 3 is all about temperature. Given a temperature, you are going to be able to calculate the corresponding temperature on another scale, whether that's Fahrenheit, Celsius, or Kelvin. The temperature of something is a measure of how hot or cold an object is compared to another object. It's measured using a thermometer, and it's reported and measured in degrees Celsius, which is what we use. It's our metric system unit. The different temperature scales are Fahrenheit, Celsius, and Kelvin. Temperature scales have reference points for the boiling and freezing points of water. Notice that right here is our freezing point of water. We know that water freezes at 32 degrees Fahrenheit, which is equal to 0 degrees Celsius, and that's equal to 273 Kelvin. The normal body temperature, here's another reference point, 98.6 degrees Fahrenheit. We're used to doing that when we take our temperature. 37 degrees Celsius is normal, 310 Kelvin. We know the boiling temperature of water is 212 or 100 degrees Celsius or 373 Kelvin. How do we convert from one to the other? Well, to get Fahrenheit from Celsius, we need to take 1.8 times the Celsius temperature and then add 32. That will get us our Fahrenheit temperature. Now to go the other way around, I would take my Fahrenheit temperature minus 32 and then divide by 1.8. Make sure you have these written down. The Kelvin temperature scale has 100 units between freezing and boiling points. So to go from Celsius to Kelvin, we just take our Celsius temperature and add 273. Now 1 degree change in Kelvin is equal to 1 degree change in Celsius. We're going to look at the difference between the freezing and the boiling points back here. Notice that the boiling point of water is 100 or 373, and down here the freezing point was 0 or 273, so the difference between the Celsius is 100 degrees and the difference between the Kelvin is 100 Kelvin. So we're able to say that 1 degree Kelvin is equal to 1 degree Celsius. Now the Kelvin temperature scale is based on 0 Kelvin. That means absolute zero. Absolute zero is the lowest possible temperature that could be achieved. That would mean that particles had zero movement, which would be equal to negative 273 degrees Celsius. 0 Kelvin, or absolute zero, has not been reached yet. We've gotten very close in the laboratory, but 0 Kelvin would mean that particles stop moving, and that has not been achieved. Here's a table looking at different temperatures and comparing the different scales, looking at the sun and what its temperature is in Fahrenheit versus Celsius versus Kelvin, and a whole bunch of other ones that you can look over. Let's do a sample problem. In a type of cancer treatment called thermotherapy, temperatures as high as 113 degrees Fahrenheit are used to destroy cancer cells or make them more sensitive to radiation. What is that temperature in degrees Celsius and in Kelvin? Why don't you pause the video here, go back, look at your equation, see if you can find it out. If you took a peek back at your notes, we want this equation to get to Celsius and then this equation to get to Kelvin. Let's plug in our Fahrenheit temperature in here. So our 113 degrees Fahrenheit minus 32 and divide it by 1.8. And we should get, when I subtract 113 minus 32, we get 81. Remember, when we report our significant figures, we look at what did they have in common, and they had the ones in common. So therefore, when I do my top subtraction, that gives me 81, which is two significant figures, and then divide it by 1.8, which is, that's an exact measurement. So I should have two significant figures in my answer. 81 divided by 1.8 should give 45 degrees Celsius. Then we go one step further and do 45 plus 273 to get 318 Kelvin. This was kind of a neat chemistry link to health, looking at the variation in body temperature. Body temperatures above 41 degrees Celsius is called hyperthermia. It can lead to convulsions and may cause permanent brain damage. Heat stroke occurs above 41.1 degrees Celsius. Treatment may include ice water bath. In hypothermia, body temperature can drop as low as 28.5 degrees Celsius. Treatment involves providing oxygen and increasing blood volume with glucose and saline fluids. Injecting warm fluids at 37 degrees Celsius into the peritoneal cavity may restore the initial temperature. Take a minute to look over Section 3, Temperature Review, and make sure that you feel comfortable with these learning goals. Section 4 is about energy. Our learning goal is to identify energy as potential or kinetic and convert between units of energy. Energy is defined as the ability to do work. It can be classified as either kinetic energy or potential energy. Kinetic energy is the energy of motion, moving energy. Potential energy is determined by the position of an object or its chemical composition. How do we know? Potential or kinetic? Water in a reservoir behind a dam has potential. So up here, this water has a lot of potential energy. When the water is released and it flows over the dam, this water is now rushing water. It is moving very fast. That potential energy is converted into kinetic energy. Heat is associated with the motion of particles. The faster the particles move, the greater the thermal energy the substance has. Think about if you had cold water versus hot water. Hot water has a higher temperature, and therefore the motion of those particles is much higher. Those particles are moving faster. They have greater thermal energy. The SI unit of energy is the joule. We talked about the SI unit of length or distance is the meter. Well, the SI unit of energy is the joule. 1 kilojoule is equal to 1,000 joules, just like 1 kilometer is equal to 1,000 meters. Let's look at this energy comparison, looking at various resources and uses. Notice way down here how much energy is used to sleep for 1 hour. So yes, it takes energy to sleep. Look how much energy we get from 1 serving of pasta, a donut, or how much energy is needed to bike for 1 hour. So if you want to eat a donut, you can bike for an hour. Either consume or release that amount of energy. And look at all the rest of these. It's pretty neat. Now, we are not comfortable using the joule. Here in the US, we are used to using units of calories. The unit calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. 4.184 joules is equal to 1 calorie. So we can then make 2 conversion factors. A kilocalorie is equal to 1,000 calories. When we read nutrition labels, for example, if it says that there's 100 calories per serving, you will notice that it's a capital CAL. And a capital CAL is equal to 1 kilocalorie. They are the same thing. Let's look at this sample problem. A defibrillator gives a high energy shock output of 360 joules. What is that quantity of energy in calories? Well, if I know that I have 360 joules, I have my 2 conversion factors. So if I have joules here, I need joules down here on the bottom. So I need to use this conversion factor, my 4.184 joules on the bottom to 1 calorie on top. 360 times 1 divided by 4.184, finishing with 2 significant figures because I started with 2 significant figures, would be 86 calories. Take a minute and look at your energy review learning goals. Make sure that you are comfortable with them. Section 5 is about calculating the specific heat for a substance, and you will be able to use specific heat to calculate heat loss or gain. Specific heat is different for different substances. Specific heat is the amount of heat in joules or calories that's needed to change the temperature of 1 gram of a substance by 1 degree Celsius. In the SI system, it has units of joules per grams degrees Celsius. In the metric system, it has units of calories per grams degrees Celsius, which is why we're either using joules or calories, and we know that we can convert from one to the other. Here's some symbols that are used in our specific heat equation. SH stands for specific heat, and that's the unit that we just said. Q stands for heat, and that's in calories or joules. M is our mass in grams, and this triangle T stands for the delta T, or the change in temperature, and that's in degrees Celsius. To calculate the specific heat of a substance, we measure the heat in joules or calories, the mass in grams, the change in temperature, which is written as delta T. And here is our equation. We can also write it linearly if you would rather. We can say Q is equal to mass times specific heat times the change in temperature. And here they solved for specific heat, so all that they did was to get specific heat by itself, they divided both sides by mass and change in temperature to get rid of those. So notice it's Q divided by mass times change in temperature, which is what they have right here. Q divided by mass times delta T. And notice they did the units here, calories or joules per grams degrees Celsius. Now the specific heat of water is 1 calories per gram degree Celsius or 4.184 joules per grams degree Celsius. Here are the specific heat of some substances. We said water's specific heat was 4.184 joules per gram degree Celsius or 1 calorie per gram degree Celsius. Notice that everything else here has a specific heat of less than water. That means that it will take less energy to heat up 1 gram of those substances by 1 degree Celsius. Here are some more. We've got ammonia, ethanol, sodium chloride. There's our water, and this is a solid water. So this would be heating up ice versus heating up liquid water. A large mass of water near a coastal city can absorb or release 5 times the energy absorbed or released by the same amount of rock near an inland city. The high specific heat of water keeps temperatures more moderate in the summer and winter. Let's try setting up a sample problem. What is the specific heat of lead in joules per gram degree Celsius? If 57.0 joules, this is our Q, raises the temperature of 35.6 grams, that's our mass, by 12.5 degrees Celsius, that's our delta T. See if you can set that up using the equation that we were given. And notice that all of the data given to us had 3 significant figures. So, of course, when I do my final answer, I need to have 3 significant figures. Make sure that when you're plugging this into your calculator, you do 57.0 divided by, and make sure that you put these 2 in parentheses when you multiply them together, just to make sure that you get the right answer. Let's rearrange the specific heat equation. Just like I showed you earlier, we rearranged here to solve for Q. So mass times the change in temperature times the specific heat. Now that it's rearranged, we can now find the amount of heat lost or gained by a substance. Let's look at an example problem. During surgery or when a patient has suffered a cardiac arrest or stroke, lowering the body temperature will reduce the amount of oxygen needed by the body. Assume this patient has 5,500 milliliters of blood and their body temperature was cooled from 38.5 degrees Celsius to 33.2 degrees Celsius. Assume blood has the same density and specific heat as liquid water. Okay, so a couple of things we need to take from that. If the density of water is 1, that means density is mass divided by volume, and we're told the volume is 5,500 milliliters. So that means that the mass must be 5,500 grams because 5,500 divided by 5,500 is 1. So I know the mass of blood. I can find the change in temperature of the blood by subtracting these 2. And then I also know the specific heat of water. It's back on that chart from up here, the specific heat of water. If we're using calories, it's 1 calorie per gram degree Celsius. If it's joules, it's 4.184 joules per gram degree Celsius. So let's plug in everything we know to find Q. Q is equal to mass times the change in temperature times the specific heat. We've got 5,500 grams, that's 2 significant figures, times that change in temperature, which is 5.3 degrees Celsius. And then it didn't specify whether it wanted it in joules or calories. So in this case, we could use either. If you wanted to use the specific heat of 4.184 joules per gram degree Celsius, that's fine. We would get 120,000 joules. They went from joules to kilojoules just because this was a big number, so they divided it by 1,000 to get 120 kilojoules. You could also have used the specific heat of water of 1. And if you did that math, you would have gotten 29,150 calories. And to have 2 significant figures, I would need to go 1, 2. That 1's not going to change that, so it would be 29,000 little calories, which is also equal to, if I divided that by 1,000, 29 big calories. Any of those answers would be fine. Let's look at another sample problem, heat exchange. We have a 44 gram piece of chromium, so this is our mass of our metal, and it is at 58.3 degrees Celsius, so this is our initial temperature. I'm going to say T initial. It's dropped into a beaker containing 20 grams of water. So this is our mass of water. I'm going to say mass of water. And the water's initial temperature is 24.6 degrees Celsius, Ti. All of the heat lost by the metal heats the water. The final temperature of the water and the metal is 31 degrees Celsius. So this is my final temperature for both. Calculate the specific heat in joules per gram degree Celsius of the chromium. Okay, so I need to find the specific heat of the metal. Let's think about this. We've got my piece of metal and we've got my water. The metal has mass, we know that. The metal had a change in temperature. We know that the metal's initial temperature was 58.3 and the final temperature was 31.0. So let's find that change in temperature. All right, so to find the change in temperature, I did the final temperature minus the initial temperature. And so the metal dropped in temperature. That's why it's a negative number, and that's okay. So we know our mass, we know our change in temperature. We do not know the specific heat because that's what it's asking us to find. And if it's asking us to find specific heat, we don't know Q at this point either. Let's look at water. Water, we know the mass of water that it's starting with. We were told that it's 20 grams of water. We know the change in temperature of the water. That change in temperature, 31.0 minus 24.6 gives me 6.4 degrees Celsius. That's my delta T. And we know the specific heat of water in joules per gram degree Celsius is that 4.184 joules per gram degree Celsius. So I know all three of these pieces. So I can find Q. And it told me that all of the heat lost by the metal heats the water. So whatever this Q is going to be equal to this Q. Then once I know this Q, I know all of the pieces except the specific heat. Then I can find that. Let's find the Q of the water. 20 grams of water times the 6.4 degrees Celsius times the specific heat of water, 4.184, should give me 540 joules. Again, that's the two significant figures. That gives me the heat gained by the water. That means, I'm going to go back here, it says all of the heat lost by the metal heats the water. So the water gains heat. The water's temperature warmed up. The metal lost heat. So that Q that the water gained, that's going to be equal to what the metal lost. So let's find the specific heat of the metal. We know the mass of the metal is 44 grams. We do not know the specific heat of the metal, but we do know that the change in temperature of the metal we said was negative 27.3, and that Q, we said that the metal lost heat. So that is a negative 540 joules. Now we just need to divide both sides by whatever 44 times negative 27.3 is. And we should get a specific heat with two significant figures, 0.45 joules per gram degrees Celsius. Check my math, go back and double check to make sure it makes sense. And then take a minute to look over the learning goals to make sure you understand this section.